This is my rocket Pioneer that I designed and 3D printed myself. I recently launched it to an apogee or max altitude of 200 feet. This is how I did it. Last October, I joined a club that was building a rocket for the American Rocketry Challenge 2026. I'd had a 3D printer for a while at that point, and my CAD skills were getting pretty good. So one day I wondered, could I build my own? I started researching if it would be possible to make a 3D printed rocket, and I saw that people had done it before, so I decided to take a shot at making my own. I structured the making of my rocket into a few steps. First, the structural design in a software called OpenRocket. Second, the CAD design in Onshape. Third, the 3D printing. Fourth, the assembly. And finally, the launch. Before I go in depth on how I made my rocket, you must first understand how a rocket like this works. On this basic sketch that's similar to my rocket, there's a nose cone, a body tube, and a fin can. In the fin can is the rocket motor, which is typically a black powder solid fuel rocket motor that you can buy pretty easily. In the rocket motor, there's a fuel that burns, a small delay in the form of slow burning fuel, and then the ejection charge. I'll take this D12 3 motor that I used in my rocket as an example. The D is the class of the motor, 12 is just the name of it, and then 3 stands for the amount of seconds of delay between the burnout and the ejection charge. In this case, there's a 3-second delay between the time the motor burns out and the ejection charge fires. The ejection charge is used to release the parachute. The charge travels up the rocket, building pressure inside the main tube, forcing the nose cone out and pushing the parachute out with it. To ignite the rocket motor, you connect it to a launch controller. When you press the button, the launch controller sends an electrical charge through the wire into the igniter, burning the igniter and igniting the rocket engine, eventually launching the rocket. The first step in building my rocket was simulating the structure of it in OpenRocket. OpenRocket is a free open source software that lets you design and simulate the basic structure of your rocket, allowing you to choose the different parameters on what you want to do to build it. I searched up tutorials online on how to use OpenRocket, and once I was comfortable enough, I decided to make my own. To build this, I needed a nose cone, a body tube to hold the parachute, and the fin can to hold the rocket motor and the fin. Because this was my first rocket, I didn't want the apogee to be too high, so I aimed around 200 feet. I paid attention to a few key metrics. First of all, the apogee, or the max altitude in the rocket's flight. Second, I paid attention to stability. The two most important metrics to measure stability are the center of gravity and the center of pressure. If you balance the rocket on one finger, the center of gravity is the point where your finger is. The center of pressure is the point where all forces act on the rocket. The center of gravity has to be in front of the center of pressure, and the stability is the measure of how far apart they are. I had to balance stability and apogee between the rocket motor and the structure of the rocket. If you ever see a race car built for the track, you'll see it has a big rear wing on the back or something else that plants it to the ground. Those cars have a lower top speed just because those parts that help in stability also reduce the top speed, so you have to balance one or the other. Originally, I had planned to make the rocket 3 centimeters in diameter, but after doing a test print, I decided that was too small for my first rocket. Once I understood how the rocket worked on a basic level, I looked for online resources to help me design it. I found a really long PDF that somebody posted of how they designed their own 3D printed rocket. In Onshape, the CAD software that I used, I started off by creating a master sketch, turning the dimensions in OpenRocket into a template that I could use for the design. I created multiple different parts: a nose cone, body tube, fin can, and motor retainer. The problem I found was that, based on my dimensions, my 3D printer can't print the fin can and the body tube in one print, so I had to figure out a way to separate them and eventually join them back together for the launch. I decided to use threads to connect everything together, and this decision required a lot of testing. I had to create multiple test prints to figure out how to make my own threads. For the centering rings that centered the rocket motor within the fin can, I had to make them print at a 45-degree angle. This is because 3D printers can't usually print perpendicular surfaces without support material, and I didn't want to use that. At the bottom, I also designed threads for the motor retaining ring. This is to hold the rocket motor inside the rocket while it's in flight. I also had to do test prints to verify the tolerance for the rocket motor to make sure that it would fit inside, and also the launch lug that would allow the rocket to slide up the launch rail. For the body tube, I also used threads to connect that to the fin can, but otherwise it was a pretty simple design. For the nose cone, I had to do some testing to make sure that my printer could print the overhang that was required for the shock cord mount. Also, in the OpenRocket design, it calls for a 25-gram weight at the front of the rocket. I had originally decided to use 5 nickels, each weighing 5 grams each, to create that 25-gram weight in the front of the rocket and implant it into the nose cone halfway through the print. However, I had a lot of struggle with this and I decided not to do that. When my dad suggested just increasing the amount of material inside the nose cone during printing, I realized that if I'd increase the infill inside the rocket, it would add 50 grams of weight. Finally, at the back, I designed the motor retainer, which I had a problem with that I'll explain soon. At this point, I was done testing and I decided to just print the parts. I printed each part pretty successfully, except for the nose cone, which I mentioned took multiple attempts to get right. The nose cone fit well with the body tube. The body tube threaded well into the fin can, but the motor retainer didn't fully screw into the fin can. The thread at the bottom of the fin can ended too quickly and didn't let the motor retainer fully screw into the bottom. Instead of wasting the fin can and printing a new one, I decided to just reprint the motor retainer, adding some extra material to the end to close the gap. At this point, the rocket was complete. All that was left was to add the parachute, shock cord, and motor. There's a formula to calculate the size of the parachute needed for the rocket, so I decided that 18 inches would be good enough. When putting that into open rocket, the descent rate after parachute deployment was low enough that it wouldn't damage the rocket, and I decided to finalize 18 inches. I'd originally made the shock cord mount in the CAD or a rope, but I realized that would be way too big for the rocket, and instead I used a shock cord from Estes. Because of this, I was worried that the parachute wouldn't come out because the shock cord mount was so high up on the rocket, but in the end it worked out. I looked online for instructions on how to properly tie a shock cord and parachute and pack a parachute into the rocket, and it worked. Under the parachute, I put some homemade recovery wadding to prevent the parachute from lighting on fire after the ejection charge. At this point, the rocket was complete and it was ready for launch. At the launch site, I assembled the launch pad. I put some tape around the launch rod so the rocket wouldn't be sitting all the way at the bottom. This would make it easier to ignite and launch. I put the igniter inside the rocket motor, capped it off to prevent it from falling, connected the igniter to the launch controller, and finally, it was ready for launch.
3, 2, 1.
Overall, the launch far exceeded my expectations. There were many things that could have gone wrong, but in the end, it all worked out. To me, while it was flying, there were a few short moments when the rocket felt a bit unstable, and now looking back on it, I could have increased the stability in the open rocket simulation. This would probably entail increasing the size of the fins or putting more weight in the front. For my next rocket, I'll try to increase the stability and pay more attention to that. Overall, I spent over $100 creating and launching this rocket. It costs a lot, but many of the things can be used again for my next launch. This rocket was very simple. It didn't have an altimeter to prove that it had gone to the apogee that was simulated. It didn't have anything fancy, so in the next rocket, I plan to create my own flight computer, and instead of 3D printing the whole rocket, I plan on using a lighter tube and a bigger motor to make it go higher. I'm extremely grateful to be able to pursue my passion and create a rocket like this, and I'm looking forward to the future. If you would like to stay tuned for my next projects, please subscribe, and thank you for watching.